Today's video, we're going to talk about exponential growth and decay. I have a few questions for you today. I'll put them on the screen so I don't have to write them out. The first question here says, a town has a population of 17,000 and grows at 4% every year. What will be the population after 12 years to the nearest whole number? So to do this, we're going to use this formula, which should look a little familiar to you. So this formula says A equals P, parentheses 1, plus or minus R to the T. Let's start with this plus or minus. We're going to decide if this is growth or decay. And because it says the population is growing, we're going to use a plus there. The R is the rate that we're growing at. So 4% is 0.04. T is the time, which in this case is 12 years. And P is the principal value, the starting value, which is 17,000. So all we have to do is type all that on our calculator all in one step. And it says round to the nearest whole number. So that works out to 27,218. That's our population. So I'm going to put P. So the new thing here is basically this formula. And you have to decide whether it's a plus or a minus. This looks pretty similar to the interest formula, but it's missing a divided by n and an n there because these are not going to have compounding quarterly or compounding daily or anything like that. So let's do the next question, number 3. A new car is purchased for $24,500. The value of the car depreciates at 14.75% per year. What will the value of the car be to the nearest cent after 14 years? So this question is the same formula. The only difference is depreciating means it's losing value. So our A is what's unknown. Our P is our starting value. Our rate as a decimal is 0.1475. And our time is 14 years. So it's the same setup. We just have to decide because we're losing value, because we're decaying, that we want it to be a minus. So let's type all this on our calculator. All as one step. And we get an answer of $2,623 to the nearest cent would be 54 cents. So that's the answer for that question. Next question. An element with a mass of 940 grams decays by 13.1% per minute. To the nearest tenth of a minute, how long will it be until there are 200 grams of the element remaining? Same formula. It's going to be decay, but this time they want us to solve for T. There are 200 grams at the end of this problem. And there are 940 grams at the start of this problem. And the rate that it's growing, whoops, this is decay, so I need a minus sign there. The rate this is decaying is 0.131. And T is the unknown, so we're going to leave it as T. So now we need to solve for an exponent that is a variable, right? I need to get this TL by itself. And to do that, when your variable is in the exponent, you have to use logarithms. So first thing, let's do 1 minus 1.131. Let's get 0.869. And then I can't do log form until it's just a base and an exponent. So this 940 needs to go away. So let's divide both sides by 940. And I'm just going to leave that as a fraction, 200 over 940. We get 0.869 t. So now we're ready for log form because I have just the base and just the exponent. So remember, to put something in log form, the little tiny base is the base of the exponents attached to. What we're taking of the log of is not attached to the exponent problem at all. It's over here. And the answer is the exponent. So the answer is the exponent. That means if I type all of that on my calculator, I will get the answer to this question. So to do log, when you have the little writing down there, you need to use the log base button. There's two ways to get there. One way is to hit math on your calculator and then scroll down to log base. So it's going to look like that. All right, or the other way to get there, some calculators, if you hit alpha pi equals, and then you use your arrow key, you can see that log base is right there. And we need a log base of 0.869 of 200 over 940. So this is what my calculator looks like. I'm going to hit enter. And this is round to the nearest tenth of a minute. So that'll be 11 minutes. That'll be 11 minutes. All right, so the answer to this whole question, if I can get it to come into focus here, is 11. 11 minutes. Time is 11 minutes. Is when we do exponential growth and decay, there's going to be the word doubling or halving, and those are very specific formulas. We actually use a different formula for that. So if your equation, or sorry, if your problem talks about doubling, we're going to use this formula. Sorry, if your equation's halving, that's the formula we'll use. And if our problem is doubling, that's the formula we'll use. So you can see halving, there's a half in there, and double, there's a double in there, there's a 2 in there. In both cases, we multiply by the starting value, and in both cases, our exponent is a fraction. The top is how long are we watching this happen, and the bottom is how long does it take for the thing to half or for the thing to double. So this question we're going to look at, number 11 on my paper, says element X is a radioactive isotope such that every 27 years its mass decreases by half. Given that the initial mass of a sample of element X is 50 grams, how much of the element would remain after 16 years to the nearest whole number? So since we're halving, we're going to use that formula. And we know the starting amount is 50 grams. And we know that it's halving. And we're waiting for 16 years, and it halves every 27 years. So the bottom of it is always how long does it take to cut in half, and the top is how long are we waiting for. So again, we just type all that on our calculator all at once, and we end up getting 33 years. All right, and I have one more example for you today, and that's my question number 23. A quantity with an initial value of 620 grows continuously at a rate of 0.3% per second. What is the value of the quantity after 0.5 minutes to the nearest hundredth? So growing continuously means that we're going to use a different formula, and that's y equals EERT. All right, so P is our initial value. So 620. E is our exponent, that our Euler's number, which we deal with when we deal with exponential growth. That's about 2.71. That's a button on our calculator. R is our rate, which is 0.3%, which is 0.003. And our time is 0.5 minutes. Now, this question says that it's growing at a rate of 0.3% per second. And it says that we're waiting for 0.5 minutes. We're mixing units. We can't have seconds and minutes. So 0.5 minutes is how many seconds? That's 30 seconds. So make sure when you're doing these questions that all the units match. So now we just type all that on our calculator, and we get 678.39. And it didn't have any units here, so we'll just leave it with no units. So that question was trying to trick you by mixing your units. If the percent is measured in seconds, then we got to make sure that how long we wait for is also measured in seconds. So that's all for today. Thank you for watching. Have a good day.